the morning of July 16, 1945, in the middle of a flat desert in New Mexico, a group of scientists huddled behind a concrete bunker and waited. They had spent 3 years building something that had never existed before, something they were not entirely sure would work, and something they were not entirely sure they could control if it did. A few miles away, sitting on top of a metal tower, was a device roughly the size of a large car. At the center of that device was a small sphere of material, dense, gray, slightly warm to the touch, that held more raw energy than anything on the surface of the Earth had ever held before. At exactly 5:29 in the morning, the device fired. The desert lit up brighter than the sun. A shock wave rolled across the ground with enough force to knock men off their feet from miles away. A cloud of fire and dust rose into the sky in a shape nobody had ever seen before. One of the scientists who watched it happen, a man named J. Robert Oppenheimer, later said that a line from an ancient Hindu text came into his mind in that moment. He said he thought of the words, "Now I have become death, the destroyer of worlds." The test was called Trinity. The material at the center of it was enriched uranium. And what happened in that desert that morning did not just change warfare, it changed the entire direction of human civilization. But the story of enriched uranium does not begin in a desert in 1945. It begins more than a century earlier in a laboratory in Europe, with a young woman working alone by candlelight, trying to understand something that nobody had understood before. Martin Heinrich Klaproth was a German chemist working in Berlin in 1789 when he examined a black mineral that miners had been pulling out of the ground for decades without knowing what to do with it. The mineral was called pitchblende, and most people considered it a useless byproduct of silver mining. Klaproth dissolved samples of it in acid and carefully isolated a new element that nobody had ever identified before. He named it after Uranus, the planet that had been discovered just 8 years earlier. He called it uranium. For most of the next 100 years, uranium was treated as a chemical curiosity. It had a few minor uses. It could give glass a yellowish-green tint that glowed faintly under sunlight, and it was occasionally added to ceramic glazes. Some pottery makers in Europe used uranium compounds to produce vivid orange and yellow colors on their plates and tiles. But in terms of scientific importance, nobody paid it much attention. It was just another heavy metal sitting on a shelf. That changed completely in 1896 because of an accident. Henri Becquerel was a French physicist who had been experimenting with a phenomenon called fluorescence, the way certain materials glow after being exposed to sunlight. He was planning to test whether uranium compounds could expose a photographic plate through a piece of black paper, using sunlight to trigger the effect. But the day he planned to run the experiment, the sky in Paris was overcast and cloudy. He put the materials away in a drawer, with the uranium compound sitting directly on top of a wrapped photographic plate, and waited for the sun to come out. When he finally developed the plate days later, just to clear out his supplies before discarding it, he found that the image had been made anyway. The uranium had exposed the plate through the paper, through the drawer, through the dark, without any sunlight at all. Something was coming out of the uranium spontaneously, something that passed through solid material and left a mark. Becquerel did not fully understand what he had found, but a young Polish-French scientist working in Paris did. Her name was Maria Sklodowska. The world would come to know her as Marie Curie. Curie picked up Becquerel's discovery and studied it with an obsession that bordered on reckless. She spent months collecting pitchblende and processing enormous quantities of the ore to isolate the sources of what she called radioactivity, a word she herself invented. She discovered that uranium atoms were constantly releasing energy on their own, without being triggered by anything external. The energy just came out of them, steadily, automatically, invisibly. In 1898, she and her husband Pierre identified two new radioactive elements hiding inside pitchblende: polonium and radium. The scientific world was astonished. Curie became the first woman to win a Nobel Prize, then won a second one in a different field, a record that still stands today. But more important than the awards was what her work revealed about the nature of matter itself. Atoms, which scientists had assumed were stable and permanent, were actually in a state of constant change. They were releasing particles and energy all the time. Some of them were slowly transforming into other elements entirely. The universe, at its most basic level, was not a fixed and silent structure. It was a living, radiating, constantly shifting process. And uranium, it turned out, was one of the most energetic participants in that process. The next crucial discovery came from a New Zealand-born physicist named Ernest Rutherford, who spent the early years of the 20th century taking apart the atom one layer at a time and figuring out what was actually inside it. By 1911, Rutherford had established that the atom was not a solid ball, as most scientists had assumed, but mostly empty space. At the very center sat an incredibly dense, positively charged core, the nucleus. Surrounding it at enormous relative distances were tiny negatively charged particles, electrons, orbiting like planets around a sun. The nucleus was extraordinarily small, but contained almost all of the atom's mass and nearly all of its energy. And it was the nucleus that was responsible for radioactivity. When a radioactive atom decayed, it was the nucleus that was rearranging itself, shedding particles, releasing energy. Rutherford had opened a door. Scientists began walking through it very quickly. In 1932, a British physicist named James Chadwick discovered the neutron, a particle inside the nucleus that had no electric charge. This seemed like a small detail at the time. It turned out to be the key that unlocked everything, because a neutron, having no electric charge, could travel through matter without being pushed away by the electrical forces inside atoms. It could walk right into the heart of a nucleus, past all the defenses that normally protected it. And when a neutron walked into the nucleus of a uranium atom, something remarkable could happen. The uranium nucleus, which had been stable, would suddenly become unstable. It would split in two, and in the process of splitting, it would release an enormous burst of energy, along with 2 or 3 more neutrons, which would then go and split more uranium nuclei, which would release more energy and more neutrons, which would split more nuclei, on and on in a fraction of a second, in a self-sustaining chain. Scientists had a name for this process. They called it fission, and the amount of energy released by a single chain reaction in a small amount of uranium made every form of energy that humanity had ever harnessed before look like a match flame compared to a bonfire. The calculation was staggering. A single kilogram of fully reacting uranium held the energy equivalent of roughly 20,000 tons of chemical explosive. 20,000 tons. From 1 kilogram, the implications were immediately obvious to every physicist in the world who understood what fission meant. And they all understood it at roughly the same moment, the late 1930s, just as Europe was preparing to go to war. Uranium, in its natural form, is not particularly useful for producing a chain reaction. And this is where the concept of enrichment enters the story. To understand enrichment, you first need to understand something called isotopes. When chemists talk about an element, uranium, for example, they are talking about a type of atom that always has a specific number of protons in its nucleus. Uranium always has 92 protons. That is what makes it uranium, and not something else. But the number of neutrons in the nucleus can vary. Atoms of the same element with different numbers of neutrons are called isotopes. Natural uranium, as it comes out of the ground, is mostly made up of 2 isotopes. About 99.3% of natural uranium is uranium-238, an isotope with 146 neutrons in its nucleus. The remaining 0.7% is uranium-235, an isotope with only 143 neutrons. That small difference in neutron count changes everything. When a free neutron strikes uranium-235, that nucleus absorbs it and splits almost immediately, releasing tremendous energy and more neutrons. When the same neutron strikes uranium-238, that nucleus simply absorbs it and becomes a slightly heavier isotope without splitting. Uranium-238 acts like a sponge. It soaks up neutrons and stops the chain reaction. Uranium-235 acts like a spark. It drives the chain reaction forward. The problem is that in natural uranium, for every one atom of uranium-235, there are about 140 atoms of uranium-238 waiting to absorb all the neutrons before they can reach the uranium-235. A chain reaction cannot sustain itself in natural uranium because the uranium-238 keeps swallowing the neutrons. If you want to create a self-sustaining chain reaction, whether to build an energy source or a weapon, you need to increase the proportion of uranium-235 in your sample. You need to push the minority isotope from 0.7% up to a much higher concentration. That process is called enrichment. And the word enrichment turns out to be almost ironic because separating two isotopes of the same element, atoms that are chemically identical and differ only in the number of neutrons in their nucleus, is one of the hardest engineering challenges in the history of science. You cannot separate them with chemistry. They react exactly the same way to every chemical process. The only way to separate them is to exploit the tiny difference in their mass. Uranium-235 is very slightly lighter than uranium-238. Slightly. The mass difference is about 1.3%. Working with that difference to sort one type of atom from the other at industrial scale was the technical wall that stood between knowing about fission and actually using it. The scientists who figured out how to climb over that wall did it under extraordinary pressure, in extraordinary secrecy, in the middle of a world war. By 1939, the theoretical groundwork for fission was essentially complete. Physicists in Germany, the United States, the United Kingdom, France, and the Soviet Union all understood what a chain reaction was and what it could produce, and many of them, especially those who had fled Europe to escape political persecution, were deeply worried about who might build it first. In August of 1939, Albert Einstein and Leo Szilard, both refugees from Europe, sent a letter to President Franklin D. Roosevelt. The letter warned that recent developments in nuclear physics made it possible, in the near future, to produce an enormously powerful chain reaction in uranium, and that Germany was likely already pursuing this technology. Roosevelt read the letter and formed a small advisory committee to look into the matter. That committee eventually grew, slowly at first, and then with enormous speed, into the largest, most expensive, most secretive scientific and engineering project in American history. It was called the Manhattan Project. The challenge was immense. Scientists needed to prove that a chain reaction was even possible at a controlled scale. They needed to figure out how to enrich uranium from 0.7% uranium-235 to whatever concentration was needed. They needed to produce enough enriched material to actually build and test a device, and they needed to do all of this before Germany did. The first milestone came on December 3, 1942, in a squash court under the bleachers of Stagg Field at the University of Chicago. A team led by Enrico Fermi, an Italian physicist who had also fled Europe, built the world's first nuclear reactor out of blocks of uranium and graphite, stacked carefully into a structure called Chicago Pile 1. Just before 3:30 in the afternoon, Fermi ordered the control rods to be slowly withdrawn. The instruments measuring neutron activity began to climb, and then they stabilized, at a level that indicated a self-sustaining chain reaction was happening inside the pile. It ran for 28 minutes. Then Fermi ordered the rods reinserted and the reactor shut down. One of the scientists present sent a coded phone call to Washington. He said, "The Italian navigator has just landed in the New World." The response came back, "How were the natives?" The scientist said, very friendly. A chain reaction was real. Now they needed the material to scale it up. The enrichment challenge was tackled on a scale that had no precedent in history. A massive industrial complex was built almost overnight in the mountains of eastern Tennessee, at a place that barely existed on any map. It was called Oak Ridge. Thousands of workers were brought in to operate enormous facilities, but most of them had no idea what they were actually doing. They operated machines and monitored gauges and followed instructions without being told the purpose of any of it. The secrecy was absolute. The two main enrichment methods used at Oak Ridge were called gaseous diffusion and electromagnetic separation. In gaseous diffusion, uranium was converted into a gas, uranium hexafluoride, and pumped through a series of barriers made of porous material. Because uranium-235 molecules are slightly lighter than uranium-238 molecules, they move slightly faster and pass through the barriers slightly more easily. After passing through hundreds of these barriers in sequence, the gas gradually becomes richer and richer in uranium-235. It is an almost impossibly slow process. You enrich the material a tiny amount at each stage, to go from natural uranium at 0.7% to weapons. Grade material at 90%. You need to run the gas through thousands of stages. The facilities at Oak Ridge that accomplished this covered more than 500,000 square feet. The other method, electromagnetic separation, used an enormous machine called a calutron. The uranium was ionized, meaning its atoms were given an electric charge and then fired through a powerful magnetic field. Because uranium-235 and uranium-238 atoms have slightly different masses, the magnetic field bends their paths by slightly different amounts, and they land in different positions inside a collector. Operators sitting at control panels, most of them young women who had been hired from local communities and given no explanation of what the machines did, manually adjusted the calutrons throughout their shifts to maximize the separation. They were extraordinarily good at it. The enriched uranium product of all this effort was given the code name Oralloy. By the spring of 1945, enough had been produced to build a device, and the device that used it, the one dropped on a city in Japan in August 1945, was actually the simpler of the two weapon designs developed during the project. It worked by firing one piece of enriched uranium down a tube into another piece, combining them into a mass large enough to sustain a chain reaction. The design was considered so reliable that it was never even tested before it was used. The Trinity test in the desert had used a different design entirely, based on a different material called plutonium. The uranium device was trusted to work on the first try. It did. The consequences of those two events in the summer of 1945 were so enormous that they are still being processed today. The world had entered an age defined not just by new weapons, but by a new relationship with matter and energy. And enriched uranium was at the center of all of it. The decades that followed the end of the war were defined by something new in human experience, the awareness that a conflict between major powers could, for the first time in history, cause destruction on a scale that threatened entire nations. The United States held an exclusive position for about 4 years. Then, in 1949, the Soviet Union tested its first nuclear device. Then, the United Kingdom in 1952. France in 1960. China in 1964. The technical challenge of enrichment had spread. And as it spread, so did a new kind of tension, one that was different from anything that had come before, because neither side could actually use its most powerful weapons without risking consequences that neither side was willing to accept. This situation produced one of the most unusual dynamics in political history. Two of the most powerful nations on Earth spent spent 45 years building ever larger inventories of weapons that both sides sincerely hoped would never be used. The weapons existed primarily to prevent the other side from using theirs. Strategists called it deterrence. The public called it the Cold War. And enriched uranium, sitting inside missile warheads and bomber payloads on both sides, was the material that made the whole thing possible, and the material that made the whole thing terrifying. But enriched uranium was not only being developed for weapons. Almost as soon as the war ended, scientists and engineers began asking a different question. If the chain reaction that enriched uranium produces could be controlled, kept just barely running rather than released all at once, could that same energy be used to generate heat, and then steam, and then electricity? The answer, as it turned out, was yes. In 1951, at a facility in Idaho called Experimental Breeder Reactor 1, scientists generated the first electricity ever produced from nuclear power. The amount was tiny, enough to light 4 light bulbs. But the principle was proven. The race to build practical nuclear power plants began almost immediately. Nuclear reactors use enriched uranium, but at much lower concentrations than weapons require. A weapon needs uranium enriched to 90% uranium-235 or more. A civilian power reactor typically uses uranium enriched to 3 to 5%. At those levels, the material is completely unsuitable for a chain reaction energetic enough to cause a large explosion. It can sustain a controlled, steady heat source, but not a runaway chain reaction. The difference between the two types of enrichment is the entire basis of the distinction between civilian nuclear power and nuclear weapons, and it is the reason why enrichment technology is monitored so carefully by international organizations. The first full-scale civilian nuclear power plant to feed electricity into a public grid was built in the Soviet Union at a place called Obninsk in 1954. The United Kingdom followed in 1956 with the Calder Hall plant. The United States opened Shippingport in Pennsylvania in 1958. Through the 1960s and 70s, nuclear power spread across Europe, the United States, Japan, and eventually much of the world. By 1979, there were more than 100 nuclear power plants operating across the globe. They generated electricity without burning coal or oil. They produced no smoke, no carbon dioxide from combustion, no air pollution from their operation. In an era of energy crises and fuel shortages, they seemed like the answer to a problem that fossil fuels were making worse every year. The fuel they ran on, enriched uranium, had a property that no fossil fuel could match. The energy density was almost beyond comprehension. A single uranium fuel pellet, about the size of the tip of a finger, contains as much energy as roughly 17,000 cubic feet of natural gas, or about 1,600 pounds of coal. A typical nuclear power plant uses about 27 tons of uranium fuel per year to generate electricity for about 1 million homes. A coal plant generating the same electricity would burn roughly 3 million tons of coal in the same period. The comparison is almost not fair to make. From a pure energy perspective, enriched uranium is in a category by itself. The decades of growth in nuclear power came with a shadow, however, and that shadow was not just the connection to weapons. It was the question that ordinary people asked very reasonably, and that engineers and scientists sometimes answered in ways that were not as reassuring as they intended to be. What happens if something goes wrong? The design of a nuclear reactor is fundamentally different from the design of any other kind of power plant. In a coal or gas plant, if something fails, you can often just shut it down and the problem stops. In a nuclear reactor, even after the chain reaction is stopped, the fuel continues to produce heat for a long time afterward, because the radioactive materials inside it continue decaying and releasing energy. This is called decay heat, and it has to be managed carefully even after the reactor is shut down. In 1979, at a plant called 3 Mile Island in Pennsylvania, a combination of equipment failure and operator confusion led to the partial exposure of the reactor core. The heat was eventually controlled, and the surrounding area was not significantly affected in terms of measurable health outcomes. But the event shook public confidence in nuclear power profoundly. Television images of warning lights and emergency crews made an abstract fear suddenly very concrete for millions of people. And then, in 1986, at a facility called Chernobyl, in what was then the Soviet Union, something far more serious happened. A poorly conducted safety test, combined with a reactor design that had a fundamental instability built into it, led to a catastrophic loss of control. The reactor's power surged to a level thousands of times beyond normal. The containment structures failed. Large quantities of radioactive material were released into the surrounding environment and spread across parts of Europe. The surrounding region was evacuated and remained off-limits for years. The response required enormous resources and affected hundreds of thousands of people whose lives were permanently disrupted. The city of Pripyat, built to house the workers of the Chernobyl plant and their families, was evacuated almost overnight and never repopulated. It still sits today as an eerie reminder, an entire city frozen in 1986, with buildings slowly reclaimed by nature, Ferris wheels rusting in empty amusement parks, apartments full of furniture and belongings left behind in a matter of hours. The Chernobyl event did more to slow the global expansion of nuclear power than any other single event in the industry's history. Countries that had been building plants canceled projects. Countries that had been planning to expand their nuclear programs put them on hold. Public opinion, which had already been shaken by 3 Mile Island, turned sharply against the technology in many Western nations. And yet, even through this period, the plants that were already operating continued to run, because the reality of nuclear power, whatever the public perception of it was that it was generating a significant portion of the electricity that modern economies depended on. In France, where the government had made a strategic decision in the 1970s to build nuclear capacity aggressively as a response to the oil crisis, nuclear power was generating about 75% of the country's electricity by the mid-1980s. France simply could not afford to turn it off, regardless of what public opinion said in other countries. The United States, which had the largest fleet of nuclear plants in the world, continued operating them even as it stopped building new ones. Nuclear power, for all its complications, had become too embedded in the infrastructure of modern life to simply walk away from. The story of enriched uranium is also, deeply and inevitably, the story of the effort to control its spread, because the same technology that produces fuel for a power reactor, enriching uranium from 0.7% to 3 or 5%, is related to the technology that produces material for a weapon, which requires enrichment to 90% or more. The difference is a matter of degree, not of kind. The same centrifuges and diffusion barriers that produce low-enriched uranium for reactor fuel can, in principle, be run longer and harder to produce weapons-grade material. This meant that any country that developed the industrial capacity to enrich uranium for civilian power also possessed a significant portion of the technical knowledge needed to pursue weapons. Managing this tension became one of the central challenges of international diplomacy after the war. The Non-proliferation Treaty, signed in 1968 by a large majority of the world's nations, was the main formal response. Countries that did not have nuclear weapons agreed not to develop them. Countries that did have them agreed to eventually reduce their inventories. And all signatories agreed to allow international inspection of their nuclear facilities. The agency responsible for those inspections was the International Atomic Energy Agency, established in 1957. The IAEA's inspectors travel to nuclear facilities around the world and verify that enrichment activities are consistent with civilian use, checking that enrichment levels are staying within the range appropriate for reactor fuel and not climbing toward weapons-grade concentrations. It is painstaking, technical, diplomatic work, and it operates in an environment where the stakes of getting it wrong are extraordinarily high. Over the decades since the treaty was signed, the system has mostly held. But there have been challenges. Some nations pursued enrichment programs secretly, without declaring them to international agencies. Some situations required years of diplomatic negotiation before being brought within the framework of international monitoring. The technical knowledge of enrichment, once released into the world, could not be taken back. All that could be done was to build systems of oversight and incentive to keep the knowledge from being used for the most destructive purposes. That work continues today in the offices of the IAEA in Vienna and in countless diplomatic conversations between governments, and it will continue for as long as enriched uranium exists. In the 21st century, the story of enriched uranium has taken on a new dimension, one that connects it back to the oldest and most fundamental questions about energy and the future of human civilization. The world is confronting the consequences of more than a century of burning fossil fuels. Temperatures are rising, weather patterns are shifting. The scientific consensus on this is clear and has been for decades. And as nations look for large-scale energy sources that do not release carbon dioxide from combustion, nuclear power, with its extraordinary energy density and its complete absence of air pollution from operation, has come back into serious discussion in a way it had not been for 30 years. A new generation of nuclear plant designs has been developed that incorporate lessons from every incident in the history of the technology. Some of these new designs use physics to their advantage in ways the older plants did not. They are engineered so that if cooling is disrupted, the reaction automatically slows down rather than accelerating, because the physics of the design works against runaway behavior. Some use different coolants, different fuel arrangements, different containment structures. Several countries that had previously moved away from nuclear power have reversed course. Japan, which shut down nearly all of its nuclear plants after a 2011 earthquake triggered a serious incident at the Fukushima facility, has restarted many of them. The United Kingdom is building new nuclear capacity for the first time in decades. Countries in Eastern Europe and across Asia are expanding their nuclear programs. In the United States, small modular reactors, compact, factory-built designs that can be deployed far more quickly and cheaply than traditional large plants, are being developed by several companies and have begun moving toward regulatory approval. The fuel for all of these reactors is enriched uranium, and the production of enriched uranium, once entirely controlled by a handful of governments with the technical capacity to build enormous enrichment facilities, has itself become a subject of strategic importance. The majority of global enrichment capacity today is held by a small number of countries, and the supply of reactor fuel to the world's nuclear power plants runs through a set of commercial and political relationships that have become increasingly significant as the role of nuclear power grows. There is also an older question that the nuclear age has never quite resolved: what to do with the fuel after it has been used. Used reactor fuel is highly radioactive because the fission process inside the reactor creates new radioactive elements that were not present in the original uranium. This material has to be stored safely for an extraordinarily long time. Some of the radioactive products of fission take hundreds of years to become harmless. Others take tens of thousands of years. The engineering challenge of designing storage facilities that will remain safe and intact over those timescales is one of the strangest problems humanity has ever confronted, because it requires building something that will outlast every institution and every language and possibly every nation that currently exists on Earth. Several countries have developed plans for deep geological repositories, facilities built hundreds of meters underground in stable rock formations, intended to contain used nuclear fuel for the timescales required. Finland has made the most progress, with a facility called Onkalo that is being cut into ancient bedrock and is designed to seal the material away with no expectation that it will ever need to be retrieved. The word Onkalo means hiding place in Finnish. It is perhaps the most serious and honest name that has ever been given to any human construction project. And then, there is the question of what comes next, not just for enriched uranium, but for the entire approach to nuclear energy that the discovery of fission made possible. Scientists have been working since the 1950s on a different form of nuclear energy, one that does not involve splitting heavy atoms, but instead involves combining extremely light atoms. This is called fusion, and it is the process that powers the sun. The fuel for fusion is not uranium, it is hydrogen, the lightest and most abundant element in the universe, and the energy released by fusion, relative to the amount of fuel consumed, is even greater than fission. Fusion also produces no long-lived radioactive waste of the kind that used reactor fuel produces. The challenge is that achieving fusion at a useful scale requires extraordinarily high temperatures hotter than the core of the sun, and containing a gas at those temperatures without letting it touch any solid material. For decades, scientists have been working on this problem, and for decades, the promise of practical fusion power has remained just out of reach. But the pace of progress in recent years has accelerated noticeably. In December of 2022, scientists at the National Ignition Facility in California achieved something that had never been done before. They produced a fusion reaction that generated more energy than the laser energy used to trigger it. The margin was small. The practical path to a fusion power plant that produces electricity for a city is still long, but the milestone was real, and it represented the first time in history that a fusion reaction had cleared the fundamental threshold of returning more energy than it consumed. Researchers at government and private facilities around the world are now competing to move from that scientific proof to practical engineering. Some of the companies involved have made predictions about timelines for commercial fusion power that would have seemed wildly optimistic not long ago. Whether those timelines hold is impossible to say, but the direction of progress is unmistakable. If fusion power does eventually become practical, enriched uranium will not be needed for the generation of electricity in the same way. But even in that future, the history of what enriched uranium did, and what it made possible for good and for ill, will remain one of the most consequential chapters in the story of human civilization. The technology that grew from Marie Curie's candlelit laboratory, through Rutherford's model of the atom, through the desperate calculations of wartime physicists, into the industrial complexes at Oak Ridge, and the reactors humming in 30 countries around the world today, changed what human beings understood about matter and energy at the most fundamental level. It changed the nature of conflict between nations. It changed the way electricity is generated. It changed the shape of diplomacy, of cities, of landscapes, of the atmosphere itself. Think about that chain of events. A German chemist notices a strange mineral in 1789 and names a new element after a planet. A French physicist leaves a sample in a dark drawer and finds that it has done something impossible. A Polish-French scientist picks up that discovery and builds an entirely new field of science out of it. A New Zealand physicist figures out what is inside an atom. An Italian physicist triggers the first controlled chain reaction under a sports stadium in Chicago. A team of engineers builds the largest industrial secret in American history in the mountains of Tennessee. And all of it leads, eventually, to a gray metallic sphere sitting in the desert pre-dawn darkness, about to light up the sky in a way no human being had ever seen before. Enriched uranium is not just a material, It is the thread that runs through the most dramatic transformation in the history of energy and power. A transformation that began with a single atom splitting in two, and that is still, in many ways, just getting started. If you found this story interesting, hit subscribe and let us know in the comments. Which part of this history surprised you the most? And make sure to like this video so more people can find it.